Hello, good morning, everyone. I'm Gaurav. We will get back to the day two of our workshop with Mr. Bhargav Joshi. And thank you everyone for being here. And let's make today's day another day of learning and inspiration. So, with this, I will hand over the meeting to Mr. Bhargav. So, I'm start.
Yeah, thank you, Gaurav. I hope everyone can hear me just fine. Okay, so I'll just share the screen. Okay, so I hope that all of you can see my screen. So yeah, today's lecture is part two of the things that we saw yesterday. So yesterday we saw Panchanga, the five elements, out of which three of them are astronomical: Nakshatra, Tithi, and Vara. And we also saw the concept of Masa, that is the month in the ancient Indian calendar. So three elements were astronomical, yoga and karna are astrological, so I did not discuss that. Today, what we're going to see is classical Indian astronomy, a brief review of Indian astronomy, Bharatiya Jyotisha. So basically, what we will cover in this talk is the astronomy of the Vedas, that is the Vedanga Jyotisha. The second part is description of the Vedanga Jyotisha and what all is included in Vedanga Jyotisha and when it was composed, in what location it was composed, and all of that stuff. Then we have Aryabhata's astronomy, Aryabhata 1, the pioneer of classical Indian astronomy. And then we have Siddhantas. So, Siddhantas is a very important concept. It's not actually a concept. Well, Siddhanta is actually a treatise. Oh, am I on mute?
No, no, you are audible.
Oh, okay. Someone said I'm on
You're
mute. Okay,
clearly
never mind.
audible.
Okay. Okay.
No, it is your other camera.
Okay. Okay. So I hope you guys can still hear me, but yeah. Okay. You're audible. Okay, great. So yeah. So I was talking about Siddhantas. So Siddhantas are very important in Indian astronomy. And then we have Indian astronomers and eclipses. So what did the Indian astronomers talk about eclipses? How did they discover the phenomena of eclipses? What calculations did they do to calculate the shadows of the eclipses? So that is a brief review of that. And then there were different yantras, tools and equipments that the Indian astronomers used for measurement. So we are going to discuss some of those. And then texts and schools of Indian astronomy, the Paksha of Bharatiya Jyotisha. And then the various eras in Indian astronomy. So we have the Kalachuri era, and then we have the Saptarshi era, and then we have Shaka era, Vilayati era, all sorts of stuff. So this is basically a roadmap of today's talk. So let's start with the first one, astronomy of the Vedas. So Ved have Shada Anga, six organs of the Ved, and they are Shiksha, that is phonetics. Then we have Vyakarana, that is grammar. Then we have Chanda, metrics. Chanda is very important if we want to recite the Vedic mantras. All the mantras or all the shlokas or all the verses in the Vedas are composed in chandas. Then we have Nirukta. So that's etymology. Basically, the etymology of the words, the language itself. And then we have Jyotisha. So Jyotisha is one of the Shada Angas of Indic literature, of Vedic literature to be particular. And then we have Kalpa, that is the rituals, all kinds of rituals that need to be performed. So Jyotisha in ancient literature is actually not entirely astronomical. It is a conglomerate of astronomy and astrology. It is a mixture of that. It has astronomical calculations, but it also features some kinds of astrological things. But we are not going to discuss that. We're just going to discuss the astronomical aspect of it. So astronomy is science, astrology is not science. And so we have Vedanga Jyotisha as the earliest text on Indian astronomy. It is the earliest Indian astronomical text from the Indic literature throughout. So let's take a look at that. In Vedanga Jyotisha, where do we find the mention of nakshatras? In yesterday's lecture, we learned what are nakshatras. Nakshatra, to revise once again, they are the divisions of the lunar orbit, and each division is a nakshatra. So there are 27 divisions of the lunar orbit, and so we have 27 nakshatras. So where do, or rather, where are the nakshatras mentioned in Vedanga Jyotisha? So these are some of the references which we find in the Rigvediya Samhita. And there are very few nakshatras that are mentioned, but some of them are Pushya, Chitra, Revati, Magha, and Falguni, which we saw yesterday in the lecture. So these are some of the things mentioned, some of the nakshatras mentioned in Vedanga Jyotisha or in anywhere in the Rigvediya Samhita. The Taittiriya Samhita, however, it gives a list of all the 28 nakshatras, including Abhijit. So usually there are 27, but an additional nakshatra, that is the 28th one, that is Abhijit, was also sometimes included in later astronomical works. So it gives a list of 28 nakshatras, including Abhijit. The Shatvat Brahmana mentions that the main nakshatras are 27 and the Upa nakshatras are also 27. I think here they're talking about the Yogatara and the other stars in that nakshatra. And then what about planets? So many people, as I explained yesterday, get confused between graha and planets. Not all grahas are planets, but all planets are grahas. So, for example, Surya and Soma, that is Chandra, is counted as a graha, but obviously those two are not planets. So just remember this correlation. So when we say planets, here I'm talking about the actual planets, not the grahas. So we see the mention of Brihaspati, and it is mentioned in Rigved. We also find the mention of Shukra. Some scholars believe that Shukra is mentioned in Rigved, and the reference is given over there. Agrahana is the beginning of the year, but that is based on the vernal equinox, which we haven't discussed yet. So I won't get into that. But approximately, if you consider that, the date of this composition goes back to 4000 BCE. This is an extrapolation if you really think about this, because this date would not agree with all the other references that we have about the Vedic literature. So 4000 BCE, you can use astronomical references to extrapolate that date, but it really doesn't agree with all the other evidences, linguistic evidences that we have, which do not go back to 4000 BCE. And there were some kinds of rituals that were mentioned, sacrificial sessions to perform the yajnas. So they also mentioned certain astronomical references in the literature. So that is what I've mentioned in that point. And then there is evidence that Atri family had some knowledge about eclipses. So basically, Rigved is a collection of poems. It is poetry, basically. Many people believe that Rigved is scientific, mathematical text and has all the secrets of the universe. It is a poetic text. It is poetry. It is rituals and incantations and poems written for the gods. So they are bardic compositions, which means poems written by families of poets. And Rigved itself gives the names of those poets which have composed every sutra or every hymn or sukta. So there is evidence that Atri family in particular had some knowledge about eclipses, but we cannot be so sure about that. And this is an interesting thing. During the Yajurveda period, it was known that the solar year has 365 days and a fraction more. This is really important. So Yajurveda period, I would say it dates somewhere between 1000 BC and between 1000 BC to 1200 BCE is the Vedic literature, the earliest Vedic literature. And the earliest compositions from Mandala 2 to Mandala 7 go back to 1400 BC. But this is very important. This says that we did know that the year has 365 days and a fraction more. So this is important. In the Taittiriya Samhita, it is mentioned that extra 11 days over the 12 lunar months needs to be added. So yesterday we saw that our month has 29.5 days. The Masa is 29.5 days. Amavasyanta system that we saw yesterday. It is measured between two successive Amavasyas. So between two successive Amavasyas, there are 30 tithis, which translates to 29.5 days. So if you multiply 29.5 by 12, you get 354 approximately. So this is interesting. It means if you if your calendar is measuring 11 days lesser than the actual time period required for the earth to complete one revolution, it means your calendar is undercorrected, right? It is measuring less days than what it should. 11 days lesser than the actual period. So this error needs to be corrected, right? Because in 3 years, it's going to measure 33 days lesser than the actual revolution period. In So this is going to create a significant error in the calendar because the sole purpose of creating the calendar was to keep it in sync with the seasons. If the calendar is not giving you the correct seasons, then there's no use of the calendar. So this undercorrected calendar had to be corrected. So after every 32.5 months, we add an entire month, and that is called Adhik Masa. So now your undercorrected calendar is corrected. So this 11 days that are missing from the actual calculation, Taittiriya Samhita does mention it about this, lack of 11 days. So a sacrifice, a yajna was performed for these 11 days. And then we see that the Vedic astronomers also evolved a system of Chatur Yuga. Now, this is very interesting because I've seen many people get confused between yuga. They believe that the huge time spans of millions and billions of years is also mentioned in the Vedic literature and Vedanga Jyotisha. We would see that it is not the case. In Vedanga Jyotisha, a yuga does not stand for millions of years. That is the Siddhantic time span. In Vedanga Jyotisha, on the contrary, a yuga is just of 5 years. That's it, 5 years. And the names of the yugas are Samvatsara, Parivatsara, Idavatsara, and Anuvatsara. And we'll take a look at that in the next slide. So this is a particular verse from Rigveda. It mentions Dirghatamas, son of Mamata, and there is a certain reference about the yuga in this particular verse. So the two intercalary months. Intercalary months is basically the Adhik Masa concept, which I explained earlier. That is called intercalation. In the Gregorian calendar, for example, we add 1 day every 4 years, the leap day. That is what we call it. That is also intercalation. Adhik Masa is also intercalation. So it does mention two Adhik Masas, that is Amaspati and Samsarpa, to complete the Yuga. And 12 solar months are mentioned in Yajurved, along with the 6 Ritus. Ritus are seasons, basically. In modern astronomy, we just have 4 seasons: winter, spring, summer, and fall. In Indian astronomy, we had 6 Ritus. I mean, the year was divided into 6 Ritus or seasons. So that's Vasanta Ritu, Grishma Ritu, Varsha Ritu, Sharad Ritu, Hemanta Ritu, and Shishira Ritu, and the months which correspond to that. Now, take a look at the names of the months. They are not the same that we saw yesterday, right? These are not Chaitra, Vaishak, Jeshta, Ashad, Shravan, Bhadrapad. These are not those names. These are the Vedic names of the solar months. So clearly, you can see a difference between the Vedic astronomy and the Siddhantic astronomy, which evolved way later during the time of Aryabhata. So this is the difference. This is what we need to understand between. This is the difference that we need to acknowledge between Vedic astronomy and Siddhantic astronomy. Vedic astronomy, I would say, was a tad bit primitive because it was way in the past. But Siddhantic astronomy is really well developed, and we will see that in the coming slides. But this is just an idea about this solar months in the Vedic literature. So now let's take a look at Vedanga Jyotisha itself, the text from the Vedic literature, which is completely on astronomy, and it is one of the Shadangas, one of the 6 organs of the Ved. So the Rigveda versions contains approximately 36 verses, and the Yajurvedic version, well, around 44 verses. And the author of this text is usually believed to be Lagat, but we are not sure if this person actually existed or this is just I mean, we are not sure if this person actually wrote Vedanga Jyotisha, because many times people used to attribute the text to some god, like Surya Siddhanta or Vishnu Smriti, Parashara Smriti, Yajnavalkya Smriti, and Brahma Siddhanta. So we are not sure if this person actually existed, and he is the one who composed Vedanga Jyotisha. It becomes very difficult to determine who are the actual authors and to whom it is attributed to. So this is quite interesting. When the Vedanga Jyotisha was composed, the winter solstice basically means the beginning of the winter season. That is what winter solstice means. Today it falls on 21st of December. So that's beginning of winter. So the beginning of winter, during the composition of Vedanga Jyotisha, it was in the constellation of Dhanishta. So Dhanishta is a nakshatra that we saw yesterday. It is in Delphinus. The Western name is Delphinus. And the summer solstice, which means the date on which the summer season begins, that was somewhere in the Ashlesha. This is also what we saw yesterday, Ashlesha nakshatra. And Varaha Mihira, an astronomer who came in the classical age of Indian astronomy, he states that summer solstice was at the end of the 3 quarters of Punarvasu. So to understand this, you need to know how the shapes of the nakshatras look, or what the nakshatras are, what are the padas, what are the quarters. So we will not get into the detail of that, but this is just for your reference, to calculate the date of Vedanga Jyotisha. So if you consider all these references, then the date of Vedanga Jyotisha comes to approximately 1175 BCE, which is very in line with the linguistic evidence for Rigved. Rigved is also believed to be this old, 1200 years before Common Era. So it is a very old text on astronomy. You can even say that it might be the oldest text in astronomy in the Asian subcontinent. Actually, you cannot say that because there are some texts in Chinese astronomy and we have Mesopotamian. But either way, this is a very old text, and we should appreciate what our ancestors have done in this text. So now let's take a look at yuga. Many people are confused about the concept of yuga. So let's see what yuga meant in Vedanga Jyotisha. So the first statement in Vedanga Jyotisha, a yuga is of 5 solar years, not 4.32 million, not 4.32 billion, not 10 lakh or 20 lakhs or all these huge numbers that you see in Puranas and Siddhantas, but only 5 years, just 5 years. And it consists of 67 lunar sidereal cycles. Sidereal means when you observe an object with certain background of stars, the time it takes for the object to come back to that location. Sidereal is with respect to the background, fixed background of stars. That is sidereal. So it has so many sidereal cycles and days and synodic months. Tithis is what we saw yesterday. Nakshatras is what we saw yesterday. And the risings of the moon. So all of this is included in a yuga, which comprises of 5 solar years. It also mentions that there are 10 ayanas and vishuvas and 30 ritus in a yuga. Ayana is basically what we know as Dakshinayan and Uttarayan. So Uttarayan and Dakshinayan are the northward and the southward journey of the sun. The sun rises exactly from the east on the day of equinox at the equator. Other times it either rises from northeast or southeast. It doesn't always rise in the east. So this shift of the rising point of the sun, that is what we understand as Ayana, Uttarayan and Dakshinayan. The sun starts moving to the north, that is Uttarayan. The sun starts moving to the south, that is Dakshinayan. So in a yuga, there are 10 ayanas and vishuvas and 30 ritus. Ritus is again seasons. So there was a practical way of measuring time, and that is a nadika, and there is also a yantra. which in the Vedic literature was Ghatika Patra, which we even see today in, if you have ever seen a Vedic marriage, like it's just any other marriage, but during the tradition or during the ritual, there is a small vessel that is kept. That is actually to measure time. So that vessel is Ghatika Patra. It measures Ghatika, but sometimes it can also be another measuring unit. But this is basically what it is in Vedanga Jyotisha. Yuga is just of 5 years. This is the key point to understand in this one. So we know the date of Vedanga Jyotisha, as we saw earlier, it is approximately 1175 BCE. So what is the location where the Vedanga Jyotisha was composed? So this is about the possible geographical origin of Vedanga Jyotisha. So depending on the references that are given in the text itself, in approximately 1400 BCE, the sun's maximum declination, that's delta, used to be about this. And this is mentioned. And the current value is about this. So the sun's declination is obviously going to change due to the precession of equinox, which we will, discuss in some later lecture. To truly understand the genius of this, you need to take an entire course in astronomy. But I'll just give you a rough idea. So I'm just telling you the formula in this case. We have delta, which is the sun's maximum declination. In 1400 BCE, it was this. Today, it is this. But that's two decimals. So that is not the value that ancient Indian astronomers used. They used the value of 24 degrees, which is fine. It's like rounding up 23.53. So that is fine. So if you use this value over here, and the accessional difference is around 18 degrees. This difference is due to the correction that needs to be applied because the astronomical positions need some correction. So actual observation and the observation predicted by mathematics. So it needs some correction. Ascension is, I will not get into that right now, right? Ascension and declination, you need astronomy background for that, but you don't need to know that for now. So you know this, you substitute that over here. This is 18 degrees. Oops, 18 degrees. So sine of 18 degrees and whatever angle you have over here, you substitute that in delta and you get phi, which is actually the latitude of the place. So that's how you know where Vedanga Jyotisha was composed. It was composed somewhere at 35 degrees latitude, so possibly in Kashmir. That's where Vedanga Jyotisha was composed, in the north. So we know the date of Vedanga Jyotisha, we know the location where it was composed, and we know the concept of Yuga in Vedanga Jyotisha and all the things that it has. So this was about the Vedic astronomy. I will not go into the details of Vedanga Jyotisha's actual Phala Jyotisha and actual ritualistic concepts because that is not relevant to astronomy. This lecture is about Indian astronomy and not astrology. So we will directly now go to the classical age of Indian astronomy that starts with Aryabhata. So there were actually two Aryabhatas, Aryabhata 1 and 2, and so that is the reason why I've written one over here. This is the one who is famous. So possibly he was born in 470 CE. You can say 500 CE Common Era in Patliputra, Patna. And he composed his first text, Aryabhatiya, when he was 23 years old. Imagine writing an entire text in astronomy when you're just 23 years old. He composed an entire text. So he was a genius. And it consists of 4 parts, which are called padas, and they are Gitika, Ganita, Kalakriya, and Gola. Usually, all the Siddhantas have these 4 parts, but Aryabhatta is quite famous because he single handedly composed an entire text, and after him, an entirely new branch or new school of Indian astronomy was started. So, yeah, he has provided notable contributions to this field. And so the first part contains 13 verses, and the remaining three parts form the main body of the text and contain a total of 108 verses. And then Aryabhata is also attributed with another work, that is Arya Siddhanta, but we have no idea where that text is. This text is mentioned in the other texts of other astronomers and also in Aryabhatiya, but we cannot actually find the text. The origins cannot be traced. So let's take a look at the first section of Aryabhatiya, Gitikapada. What does that have? This is where the large units of time are introduced, the huge values that you have in the Puranas, like Kalpa, Manvantara, Yuga. 4.32 billion years is Kalpa, that is one day of Brahma, and Brahma lives for 100 such years. So his total lifespan is 155 trillion years up till now, and Brahma lives entirely for 311 trillion solar years. So these huge numbers that we have, they do not exist in the Vedic literature. As we saw earlier, in Vedic literature, in Vedanga Jyotisha, a yuga is only of 5 years. These huge values of millions of years, they come in Siddhantic period, basically from Puranas. So all these large units of Kalpa, Manvantara, Yuga, Kalpa is 4.32 billion, Manvantara is 307 million years. Yuga has varying values, but this is Kali Yuga. Remember, again, in Vedanga Jyotisha, Yuga was not this high. Yuga is only 5 years in Vedanga Jyotisha. Okay, and what else does it have? It has degrees and minutes, which is very much required in not just trigonometrical calculations, but also to measure the actual planetary positions. And then we have the linear units, that is yojana and hasta and angula. Yojana is the unit of distance. And the construction of the tables of Jya or Ja. So this is very interesting. This is a trigonometric sign, which is unique to India. I mean, the invention was made independently. It does not depend on other cultures. This was made independently by Aryabhata by using a totally different method than what the Greeks used or what the Chinese astronomers used. And the most important thing is the tables are summarized in just 10 verses. So this is again another genius aspect of Aryabhata to calculate the values and to put them up as tables in just 10 verses. So this is another aspect of Aryabhata which makes him brilliant. Then we have Ganitapada. As the name suggests, it requires mathematics. So it contains 33 stanzas. A general solution to the first order indeterminate equations is given in Ganitapada of Aryabhata. This is 476 CE. Very early. So this is something that needs to be appreciated. This is brilliant. So it laid a strong foundation for all the later astronomers to learn astronomy, to apply the methods, to use mathematics, maybe to perform corrections. So this was a very important thing that he did. And finally, the third section is Kala Kriya Pada. So again, it consists, so if you see Kala Kriya, split the word Kala, so it has units of time. So that hence the name. And it also gives the method to determine the position of planets for a particular day, any day of the year. And yeah, he gives the calculations for Adhik Masa and Kshaya Tithis. We saw the concept of Tithi Kshaya yesterday in the lecture. So he gave the method to calculate anything regarding Adhik Masa and Tithi Kshaya. And he also gave the method to calculate the angular speeds of the planets. This is very important. The concept of weekdays are all included in this part of the text. We do not find this mention in Vedanga Jyotisha, if you remember. There was no mention of this. So again, to emphasize the concept, in Vedanga Jyotisha, the astronomy was kind of primitive, but from Aryabhata, the astronomy gained an impetus. And that's what we see here. It started flourishing throughout the Indian subcontinent. Finally, we have Golapada. So spherical trigonometry is included in this thing. It is very important. And yes, Aryabhata's work was based on geocentric ideas, but some of his texts do give a hint that he was trying to propose heliocentrism. He did not, but he was trying to propose that. So Golapada mentions has 50 stanzas, and it has very important information about chronometry, how to create a calendar and what is the starting point of that calendar. So it was Aryabhata who actually gave the value of the Kali Yuga, the beginning of Kali Yuga, as this. This is Aryabhata's date of Kali Yuga, the beginning of Kali Yuga. So we find that in his text, Aryabhatiya, and he was the one who proposed that. And there are two systems. In Audayika system, Kali Yuga begins with Uday at Lanka. Lanka is not Sri Lanka or Ravana's Lanka. Lanka is actually one particular position in India where astronomical observations were taken, and that was a reference. The other one is Ujjain. So Ujjain and Lanka are two reference positions. And in Ardharatrika system, it begins at midnight at Lanka. So this is important. These are two different systems that he used, depending on which the beginning is marked by different intervals. So yeah, this is Golapada. So what were Aryabhata's innovative contributions? So this is actually important. You might have seen many Instagram pages making ridiculous claims about quantum physics and all that stuff being invented in Vedas, but they don't actually mention the contributions that astronomers have provided. Actually. So these are some of the innovative contributions that he did, which none of the people actually try to read and mention anywhere. And that is quite disappointing, to be honest. So he gave a unique method of representing huge numbers, and this was for the purpose of metric. So this was quite an interesting contribution. He gave sine tables, again, very important. The third point is especially important. Earth is spherical. He proposed that. Um, well, the sphericity of the Earth was also proposed in Greece in 300 BCE. That's 800 years before Aryabhata. But Aryabhata in the Indian subcontinent independently proposed that Earth is spherical without any borrowing from Greek astronomy. He came up with this all by himself, by his own observations. He did not use the method that Greeks used to determine the diameter and the circumference of the Earth. I mean, the Eratosthenes and Aristarchus of Samos. They also did that in 300 BC in Greece, but Aryabhata did that on his own, from his own observations. So, Bhugola Sarvato Vritta, it is circular in all directions, so it is spherical. And this is the shlok, which you can read. And in this case, we are going to see how he used this to perform his calculations. There's an entire chart. I think it is there in this PPT. If not, I'll just share that on my Instagram page in the story. But yeah, so here what we see is he gave the period of one sidereal rotation. And look at the accuracy of the duration of the day that he gives. Extremely accurate. So this is admirable. This needs to be appreciated. This is the thing that people need to know. And this is the thing that we should be proud of. He did that all on his own by observing the stuff on his own and then performing the calculations by himself. This is admirable. This should be appreciated. So this was all about Aryabhata, right? Aryabhata was the pioneer of Indian astronomy. It is very important to know about Aryabhata when you learn astronomy. He's the pioneer of classical Indian astronomy. But then what about Siddhantas, right? So Aryabhata himself composed Arya Siddhanta, the origins of which we don't know, but Aryabhatiya is, you can download that PDF anywhere. It's available free as a free PDF. So then it comes to Siddhantas. So what exactly is a Siddhanta? A Siddhanta is a full-fledged astronomical treatise, as I have mentioned, right? So to give you an idea, there were three types: Siddhanta, Tantra, and Karana. Karana and Tantra were kind of, less advanced texts. They were meant for the layman and for the everyday astrologer. A Siddhanta is meant for the astronomer who is like a scientist. He's a researcher. He is the one who creates those values and calculates those values. So a Siddhanta is like a full fledged astronomical treatise which actually creates the formulas and stuff that the later astrologers use. Modern day astrologers even today rely on Arya Pakshas. Some astrologers do, some of them go to Saura Paksha. But basically, Siddhanta is a PhD thesis, to be particular, or it is like a very highly known reference book from which all the other books are written. So that is what a Siddhanta is. Siddhanta is highest, the most complex in astronomy. After that comes Karana, and then comes Tantra. Now, this is interesting. The cosmology of the Siddhanta has some features from the Puranic universe. So, this is where we see the effect of the Puranic mythical tales in astronomy. So this cosmology does not mean the cosmology that we have in physics. Cosmology, that is cosmology with a capital C. In this cosmology, in the philosophy of religion, means an explanation that is given by religion about nature or about the universe, about the world, how it came into existence. They're usually mythical tales, mythological tales, but they did have an influence on the cosmology of Siddhanta. There were 18 Siddhantas, allegedly, but today we only know of five, which were compiled by Varahamira in 5th century, in 6th century CE, actually. Those are called the Pancha Siddhantika. So it has five Siddhantas, as the name says. So in Siddhantas, there is a chapter called Adhikara or Adhyaya, right? There are different Adhyaya, chapters, basically. So one of them is Madhyamadhikara, that is a chapter to calculate the mean positions of the planets, right? An example here is according to Surya Siddhanta, the Nirayana. Nirayana is without Nirayana precession, without actual precession. Sayana is when you consider actual precession. What is actual precession? Google it. I won't explain that right now because we don't have enough time, but it's very easy. I mean, you can easily Google that. It is a modern astronomical term. It was known to ancient Indians and also to Greeks. And sometimes some references also say that Chinese people also knew about actual precession. So we have Nirayana solar year. And if you use the formula that is given in Surya Siddhanta, this is the value that you get for 1 year. Look at the decimals. How many integers or how many, let's say, significant figures are there after the decimal? A very accurate value that is given. Again, something to be proud of. This is, I guess, the age of Surya Siddhanta might be around 505 CE at least. So in 505 CE, they were able to accurately calculate the duration of the year up to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. That's admirable. That is something, again, that should be appreciated. The second type of adhyaya, which is featured in every Siddhanta, is Spashtadhikar, true position of the planet. So mean position of the planet and the true position of the planet are important because the mean position does not incorporate Vakragati. Vakragati is the retrograde motion. The planet suddenly starts moving backward. It appears to move backward in the sky. That is Vakragati. True position helps us to calculate the actual position of the planet considering all the five gatis of the planets, or the grahas to be particular. And the people who used to convert Madhyagati into Spashtagati, or Madhya position into Spashta position, they were called Jyotishi. That is what they used to do. And the name later started being mispronounced, and those people became Joshi. That is what I am. Yeah, but those people performed the calculations to convert Madhyama to spashta. Just remember the difference. One is mean position, the other is true position. So yeah, it gives the procedure to obtain the true position of the planet from the mean position. The two corrections that are described are manda and shigra. So what is manda? So basically manda corresponds to the equation of center. We have the equation of center of the sun, equation of center of the moon, equation of center of the earth. And by using these, we can also apply this methodology to understand eclipses. So it basically means equation of the center. That is what manda is. Shigra is to convert heliocentric positions of the planets to geocentric. This itself implies that they were considering heliocentricity and to convert that into geocentric. So you have to apply the second correction. When you apply these two corrections, you can convert from mean position to true position. Right? So that is chapter 2. And finally, the third chapter, which is there in every Siddhanta, is Triprashna Adhyay, 3 questions. It deals with 3 questions. So what are these 3 questions about? They are about direction, place, and time. How to know the direction, at what location you're taking the observation, and the time of the observation, or any other things related to these 3 questions. So it entails the procedure of finding the latitude of the place, times of sunrise and sunset. This is something interesting which we will see in the upcoming slides, and the calculation of lagna. Lagna in Marathi means marriage. That is not what it means here. Lagna is the rising point of the ecliptic in conjunction with the celestial equator. It's kind of complicated, but if you do have a background in Indian astronomy, this is pretty straightforward. That is what Lagna means. So these are the 3 chapters that every Siddhanta has. Madhyama Adhyay, Spashta Adhyay, Triprashna Adhyay. 3 chapters in every Siddhanta. And then those 3 chapters have sub-chapters. For example, in the Triprashna Adhyay, we have chapters on yantras, which we will see in the upcoming slides. And so we have Chandra and Surya Grahanadhikara, computations of lunar and solar eclipses. That's pretty obvious because Indian astronomers did study the eclipses. Effects of parallax. That is what I'm going to explain next. Very important, very interesting. And minor deviations between computations and observations, whatever they are noticed, they are calculated, included in the tantras, in the karana, to give accurate results. So let's take a look at what Indian astronomers believed about eclipses. Moon covers the sun and the greatest shadow of the earth. This is from Aryabhatiyam. At lunar eclipse, the moon enters the shadow of the earth, and at solar eclipse, the moon enters the sun's disk. So clearly, they are able to provide a natural explanation for eclipses. Remember, they're not saying anything about ill omens or, eclipse is bad for health. They're not saying any of this. In fact, in the next slide, see what Varamira says. This is the biggest proof that ancient Indian astronomers did not consider eclipse to be something bad or some ill omen. Look at what he says. An eclipse by no means to be ascertained through omens and other indications, because the portents such as fall of meteors and earthquakes occur at other times also. There is nothing bad about an eclipse which leads to some, bad events. There is nothing like that. It is all pseudo. Varahamira himself is saying this. See what he says next in Bruhat Samhita. Scholars should not believe in the following myth of the ignorant to the effect that an eclipse cannot take place except when there is a combination of 5 planets. So this is more like debunking the astronomical position that other schools held. That is what he's doing here. But again, see what it says here. So if you just read this entire sentence, I'm not going to read it out loud, but it's pretty clear. They are trying to debunk the myths about eclipses. They don't believe that eclipses are anything bad. But unfortunately, people in India still do believe in that pseudoscience. So that is something horrible. and something that's utterly disappointing. So this is Brahmagupta's work on eclipses. So it gives a formula to calculate the diameter of the bodies and also the diameter of the shadow that is cast during an eclipse. So when you do this, you get the diameter in arc minutes. When you do this, you get the diameter of the shadow. And this is from Khanda Khadyaka, that is Brahmagupta's treatise. So partiality and totality just means a total solar eclipse and a partial solar eclipse. How to distinguish between the two, and when is it a partial eclipse and when is it a total eclipse. So he gives a method in this, which you can again read at your leisure later. Maybe I'll share the slides. This is something that I want to discuss. So parallax. This is quite interesting. So you do this experiment on your own. Close your left eye and hold out your finger and point towards some star. Do this experiment on your own. Close your left eye, keep your right eye open, and point towards some star in the sky. And then open your left eye and close your right eye. You'll see that your finger has moved and it's no longer pointing at that star. This error is called lambana, parallax error. So let's see what happens here. E is the center of the Earth and M is the center of the Moon. Now, during calculations, the two centers are considered. But an observer standing on the surface of the Earth is not exactly at the center. So that distance is going to create some kind of a parallax. So let's say if the observer is standing at this location, if you join the line between the two centers, and if you join the line from O to M, it subtends an angle. This angle needs to be corrected, and this angle is called lamban or parallax. This concept is also used in modern astronomy, by the way. So this is interesting. And this is an error that needs to be rectified, and the Siddhantic texts give a method to rectify this error. So now if you move this arc all the way up, in this direction, when the sun and moon are directly overhead at zenith, there is no parallax because all the lines are coincident. So directly at 90 degrees, there is no parallax. Directly at 0 degrees, there is no parallax. Whereas at 90 degrees, we have the maximum parallax. So that is lambana. And Bhaskara gives the same description of the parallax. We see the same thing. We have E, that is the center of the Earth, Moon, the Sun, and the observer. So as this S would move in a circle, at this position, the parallax is 0. In here, max parallax. Quite easy to understand. It's all geometric, and it's when you draw a schematic like this, it's even easier to understand it. So now we are coming to the end of the talk, almost at the end. So there were certain yantras that they used to perform these measurements, to take the observations. So these are some of the yantras that are mentioned. Shanku yantra, Yashti yantra, Chakra yantra, Dhanur, Ghatika, Chaya, Shakata, Kartari, Pitha. Some of the yantras, the instruments that they used. Let's take a look at those. So we have Shanku yantra. Shanku is this object. Oops, sorry. A gnomon was placed. If you place a gnomon, what you have to do is see where the sun rays meet this point and cast a shadow on the ground. So when you do that, if the sun rays are falling like this, mark a point where the shadow of the top of the gnomon is cast. This is before the noon. Let's say at 11 a.m., the shadow is at this place. And at 1 p.m., 1 p.m. after noon, and this is before noon. This is 12 p.m. exactly. So basically, plot the point which gives the shadow before noon and afternoon at equal intervals of time. When you do that, join this line and draw a perpendicular bisector to that. That perpendicular bisector points is actually the north and the south direction. And draw a perpendicular bisector to this, and that gives the east-west direction. So just by using this, a stick, you can find out all the four directions simply by marking the tips of the shadows. So this method was invented by ancient Indians, also by Greeks. Gnomon is what it is called in Western astronomy, also by Chinese and Mesopotamians. But India developed it independently, as we will see. So yeah, a simple instrument that can be used to, find out all the directions simply by using the concept of shadows and trigonometry. This is Chaya Yantra. So the sun's rising point and setting point, these are measured, and this actually helps us to know if it is Dakshinayan or Uttarayan, and this helps us to know the declination of the sun, which is kind of important for astronomical measurement. So this is what they used. Then we have Yashti Yantra, which again gives the altitude of the sun. Then we have Shakata Yantra. This is used to measure the tithis. So yesterday a person asked, how does a common man know what tithi it is? This instrument can be used to know the tithi of the day. So when you extend this line, the distance that we have here, and extend that on a circle, this distance, convert that into degrees, and that is the tithi of the day. And all you have to do is take one arm of that and point it to the sun, the other arm of that point it to the moon. Whatever the angle is subtended, that is the tithi of the day. As simple as that. So even a layman can use this instrument. So this is the Shakata Yantra. Looks like a Shakata. Shakata is basically a V. So that's Shakata. Then we have Aryabhata's Chakra Yantra. So what you have to do is mark where the sun rises. That's the point over here. And the sun is going to rise in the sky, right? So this is east. Perfect east that we have on the day of equinox. At other times, the sun is either going to rise from the north of east or the south of east and sets into north of west or south of west because we have Uttarayan and Dakshinayan. But it can also help us to know the altitude of the sun, how high the sun is in the sky. And you have to look through here, and that gives you the location, and this angle is the altitude of the sun. So azimuth and altitude. Dhanuryantra is again the same, except with the difference that there's a small gnomon that is attached to it, and the shadow casts on the ground, and it helps you to give the agra is what it is called. But that's too much into astronomical. So we will not really discuss or go into detail regarding what is agra and stuff. But this Dhanuryantra looks like a dhanusha. Oops, sorry. And Ghatika Yantra, this is what you see even in the rituals. The next time you attend a wedding or a threading ceremony that is being performed as per the Indian tradition, try to see this in that ritual. It measures the Ghatika, and Ghatika is required to know what Muhurta it is. So yeah, this is a basic instrument. It has a small bowl, it has a hole at the bottom, and it is, it is floating on water, and there's a bigger vessel. Water is slowly going to go inside, and this is going to go down. The time that it takes for the small vessel to reach the bottom, that is Ghatika. So you convert Ghatika into Murta, one Murta has ended. Again, The water is emptied, kept on top, it goes down, second vertical. Pretty easy. It's like a water tank with a leak or a small tube that is protruding with a certain diameter. As simple as that. And this is used in all the Indian weddings and also in threading ceremony. Just see that the next time you attend any wedding. And finally, we have the schools of Indian astronomy. So these were the three schools of Indian astronomy: Saurapaksha, Aryapaksha, Brahmapaksha. Sauryapaksha had Surya Siddhanta as their prime text. Aryapaksha is based on the works of Aryabhata. Arya Siddhanta is their prime text. And Brahmapaksha is based on the works of Brahmagupta. And Brahma Siddhanta is their prime text. And sometimes they disagreed with each other on some of the things, so they were not always in agreement with each other. And these are some of the texts that you see which were composed by the astronomers in the respective pakshas. So we have Varahamira, who belonged to Saura Paksha, Grahalagava by Ganesh Daivadnya. That was a pretty recent text that was composed, 16th century, that is like during the time of maybe a little before Newton. Then we have Lalla, who belonged to Arya Paksha, and then we have Brahmagupta himself, who composed Brahma Siddhanta. Rajamruganka is another text. Siddhanta Shiromani is by Bhaskara. And Karana Kutuhala, that's another text. So all these are the texts of Indian astronomy, classical Indian astronomy. They are ingenious. You should read them once if you have the time. So what are the other texts apart from Siddhanta? Siddhantas are huge, full-fledged astronomical treatises. So what are the other texts? We have Karana, which are simply astronomical handbooks. Then we have tables, which can be used by any village astrologer or astronomer to know the tithi, to create the panchang, to read the panchang, and all that stuff. So that's tables. Then we have calendars, panchanga, actually what we learned yesterday. Three of them astronomical, two astrological, angas. Then we have a book on omens, Samhita. This is again, this is not scientific, this is astrological. Then we have Hora, Jataka, horoscope. Genethliology is again a pseudoscience. Horoscopes are not really scientific, but yeah, that's a part of astrology. And then we have cathartic astrology and interrogational astrology. Again, as the name suggests, it's astrology, so it's not really science, but it's included in the texts. So as I said in the beginning, Jyotisha is a mixture of astronomy and astrology. There was no distinction between the two as it exists today. And finally, we get to the end, the various eras, the various types of calendars that were used. We have Kali Yuga, Saptarashi Kala, which was used in Kashmir. This is based on the Saptarshis, the motion of the Saptarshi. There's an asterism in the sky called Saptarshi. There are 7 stars in it. In the west, it is called Big Dipper. It is a part of Ursa Minor constellation. And the 7 Rishis, which are the Saptarshis in them, are Kratu, Pulaha, Pulastya, Atri, Angira, Vashishtha, Mariji. And Vashishtha has his wife Arundhati, which is also a star in the sky, right next to Vashishtha. You can all see them with the naked eye. Then we have the Vikram era, which was used in Gujarat, North India, and Bengal. And then we have the Shaka era, which is very famous, And then we have Vilayati era, and then we have lunisolar firstly year. So all these are different types of calendars that were used. And Shaka era is actually Purnimanta. So yesterday we saw the difference between Amavasyanta system and Purnimanta system. In the Purnimanta system, the month ends with Purnima. In this calendar, there is no distinction in the form of Shukla and Krishna Paksha. So that's quite interesting. So finally, this is what we end with. This is a quote from Vedanga Jyotisha, which talks about the importance of astronomy. It says, like the crests on the heads of the peacocks, like the gems on the hoods of cobras, astronomy is at the top of the Vedanga Shastras, the auxiliary branches of Vedic knowledge. So with this, I would like to end my talk, and I'll stop screen sharing. And if you have any questions, now is the time. Are there any questions?
There are some questions in the chats, just like yesterday. Just
Oh, okay. Yeah. Let me check the chat. Okay, please do share the recording as well as slides. Yeah, I'll send this PDF to Bharatiyan. There is some difference between the Panchanga followed in northern states and the one followed in, say, Maharashtra. Do you know why that is? Yeah. So there is a difference, and the difference could be due to Amavasyanta or Purnimanta system. The difference could also be due to the era that they are using. The difference could also be based on the text that they consider to which paksha they belong. If they are using the calculations from Saura paksha, they most likely follow the Surya Siddhanta. If not, they are either following the Arya paksha or Brahma paksha. So yeah, there are many texts based on three schools as we learned right now. And how yojana is calculated and why it is between 5 to 9 always. So the values of yojana are different in different texts. It is not fixed, and different texts give different values. There is no agreement on what the value of yojana actually is. And why did Aryabhatta take 4, 3? Okay. Um, the reason why he took this is because all the heavenly bodies that he was observing, they have a conjunction, he believed, after these many years. A conjunction where all the planets are in the same Rashi, which is very unlikely. I'm not sure if that actually happens after this time period, but that is what Aryabhatta believed, depending on the Puranic values that he used. And where exactly is the Lanka? So I'll tell you the exact coordinates of Lanka. Maybe I'll upload that on my story. I don't recall them right now, but Lanka and Ujjain were the references that were used for astronomical observations. That's not the Lanka of Ramayana or Sri Lanka. Did India follow a daily dating system like we do today before the Gregorian calendar to mark day-to-day events and date important historical events? Yes, it did. So that's what the Purnimas were. So in yesterday's talk, we saw that with every Purnima, a festival was associated. So they did follow a daily dating system, but the day here is not the solar day, not the divasa, but tithi, right? Not the divasa, not the solar day, a lunar day. His and modern calculations have a little difference. Yeah, they are obviously going to have difference because Aryabhatta used a geocentric system and modern astronomy is heliocentric. And none of the ancient Indian civilizations knew about Uranus and Neptune. So it's impossible for them to have these calculations or considered these calculations in their system. So yeah, obviously there's going to be a difference in that case. But the values for um, the revolutions of the moon, the revolutions of the sun, eclipses, duration of the day, duration of the year, those are very accurate and in line with modern astronomy. Someone raised a hand right now. You can just unmute yourself and ask the question if you have. You don't need to type that in the chat box. Okay, what indications we have from Vedic astronomy that it follows the solar calendar system? So actually, Vedic astronomy does not really follow a solar calendar. It follows lunisolar calendar, right? Not lunar, not solar, lunisolar. Moon and the sun are important. Both of them are important. That is why we have the concept of tithis and nakshatras and lunisolar months, which are around 29.5 days in duration. What is Vishuva? Vishuva is basically there are different um, astronomical parameters like ionic vrutta, Vaishuvik vrutta, celestial equator, basically. So that is what Vishuva means. But that is, you'll need to know some basics about Indian astronomy before I can explain that. Is Aryabhata's work also based on geocentric? Yes, it is based on geocentric. Although he did try to propose heliocentrism as an idea. Gupta period, a lot of trading between Vedic times and this era. So a lot of cultural knowledge exchange could be possible. Yes. In fact, there was a cultural exchange between Greece and India. Much of the astronomy that we know today as Indian astronomy was actually borrowed from the Greek astronomy. The concept of days of the week, as we learned yesterday, it is borrowed from Greeks. The concept of rashis, which most of the people are oblivious to, is not an ancient Indian concept. It is actually a Greek concept of zodiac. Ancient India did not use rashis, they used nakshatras because our calendar is lunisolar. It depends more on the moon than it does on the sun. Any other questions? I don't see any more questions in the chat box. Okay, I guess all the questions are done for today. If you have any more questions, you can just unmute yourself and then ask the question. If not, then we can conclude for the day.
Hello.
Yeah.
Yeah, but one question I had, like you mentioned that we now we are able to calculate the exact time and date for Vedang Jyotisha. With reference to that, have we also identified the dates for Puranas? Because we have many Puranas, 18 Puranas and Uppuranas, and there are lot of reference. The stories actually are similar to what we have in Greek mythology. The stars and everything we create the, that's why they are called mythology in the large in the scientific temperament, you can call them. So are there any specific dates for these Puranas as well based on these observations?
So the Puranas don't really feature astronomical observations so that we can calculate the dates, but linguistically, the
Mm,
Puranas are somewhere between 3rd century to 10th century CE.
okay.
They're pretty recent.
Mm, okay,
Yeah.
thank you.
Yeah, no problem. Any other questions?
Hi, Bhargav.
Yeah.
Somebody is saying about Kojagiri Purnima that you said you mentioned today.
Oh, yeah. So the Kojagiri Purnima is actually a supermoon. And it also occurs, let me go back to actually the slide. Let's see if I can access it again. Hindu Panchang, yesterday's lecture, Kojagiri. Let me check the date. Oh yeah, so basically the Kojagiri is highlighted simply because it is a supermoon. In that Purnima, the moon is brighter, but it's also bigger. So that's why Kojagiri is highlighted. It's just supermoon. That's it. It was a supermoon. It was also there recently. It keeps on occurring after periodic intervals. So yeah, it's not really something astrologically special. Just a supermoon. That's it. So
Also
yeah,
one
Hi,
more thing, sorry.
please speak.
Yeah, thank you. So the geometry part, which we have, as we saw that we the ancient Indians used the geometry quite uh, uh, means it means it has lot of detailed calculations and a very evolved geometry, you can say. So there is also this they say that geometry originated, but you said that the similar we can also find in Chinese and Greek and Mesopotamian cultures. So are there traits of geometry in those cultures as well?
yeah, of course. So Greeks were also pretty advanced in mathematics. In fact, I would say I would make the bold claim that Greeks were more advanced in geometry because Greeks were more focused on natural philosophy than Indians were. Basically, the reason why ancient Indians used all of this was to relate it somehow to religion. But Greeks did not have a structured religion as such. They were more into natural explanation of things. They had certain weird ideas in metaphysics, but they were more natural philosophers. And yes, so Greek astronomy also has heavy influence of mathematical calculations. And we do see that in Zeno, in Pythagoras, Archimedes, and mathematicians were a whole category of philosophers in ancient Greece. And if you take a look at, so this is basically Surya Siddhanta. I have the hard copy. This
Mm,
entire book is filled with formulas and everything. So you can
yeah,
just go through this book. You'll find everything about Indian astronomy in this.
yeah,
Yeah.
thank you.
Yeah, no problem. I
Hi,
guess one
Bhargav.
more person had a
Thank you for
question.
this knowledge. I
Yeah.
have one question only. So, once upon a time,
Mhm.
I read a book called Awakening Indians to India by Chinmaya Mission. So there it was
Mhm.
mentioned that Aryabhatta figured out the distance between Earth and the Sun, and the modern day calculations, the difference is only 30 kilometers or so. So are you aware of it?
Yeah, of course. I mean, calculating the distance between the Earth and the Sun, it depends on the angular diameters of the Sun and the Moon. If you don't know the distance, you cannot know how to calculate the shadows of the eclipses. In fact, not just that, he also calculated the diameter of the Sun, and that was also done in ancient Greece. It's actually pretty straightforward because we can see the Sun every day, and we can see the basically the northward movement and the southward movement, and how the sun looks at different latitudes. Where is it at the equator? Where is it at the tropics? So yeah, he did do that, and even Greeks did that, and even Chinese did that. Maybe not Chinese, but Greeks definitely did that, and Mesopotamians later did that. So yeah, it is admirable, but it's nothing out of the extraordinary. I mean, out of the ordinary. It is admirable, something that definitely needs to be appreciated. Let me check the chat box if there are more questions. No, so Kojagiri is not inevitably a supermoon, because our calendar is lunisolar. So sometimes it is out of sync from the Gregorian calendar. So it's not going to be always a supermoon, but it's going to be a Purnima for sure. Any other questions? Okay, I guess then we are done for the day. We can conclude with the lecture.
So as we wrap up our session today, I want to thank each and every one of you for being a part of this workshop. And really, Bhargav's insight have been enlightening, and I hope you leave here with inspired to continue your own learning journeys as well with whatever insights he has given to you. And I hope you all have noted it down as well. So thanks, Bhargav, and all of you for joining us today and yesterday as well. And be curious and keep exploring. So we will be conducting more such workshops in the future also. So stay tuned for such such opportunities ahead as well. Thank you, everyone.
Yeah, can you please do share these sessions?
Yes, we will definitely
Yeah.
be uploading it on the YouTube, and we will be sharing it as well. So you can just follow us, like you definitely follow us on Instagram. So you can check our story once it's uploaded. We will be posting it on our story as well, so you can access it from there.
Okay, thank you.
Yeah, thank you, thank you.